All right, great. Okay, so let's get started. Hi, my name is Louisa. I will be the MC today for Apurvaa's talk. This is Apurvaa Subramaniam, and she will be presenting on data literacy in the age of misinformation. She's also currently a senior data scientist at Instacart. So take it away.
Thanks, Louise. Hi, everyone. Thank you for attending my talk today. I truly believe that data literacy is a pressing topic that needs to be talked about more. So let's jump right in. What is data literacy? According to Wikipedia, it is the ability to read, understand, create, and communicate data as information. So it has three main components, which you can see in this Venn diagram here. And the focus of my talk today is this green circle, which is reading data. More specifically, the ability to read and interpret summary statistics in everyday media, such as graphs, tables, statements, surveys, and studies. So why is data literacy important? There has been an explosion of data in the past few years. And here are some statistics to give you an idea of the massive scale at which data has been growing. So Google gets over 3.5 billion searches daily. Internet users generate about 2.5 quintillion bytes of data each day. And quintillion has 18 zeros, so it's an enormous number. So today we have more access to data and information than ever before. However, this has also led to a rise in misinformation. I'm sure a lot of us can relate to this image. This is how a lot of us felt during the pandemic, when we were bombarded with information, but often not sure what was accurate. Several polls and surveys on this topic also reflect this. So this statistic is from 2021, where only about 29% of US adults say they have a great deal of confidence in medical scientists to act in the best interests of the public. And this is down from 40% who said this in November 2020. Here are some famous examples of misinformation. In 1998, Andrew Wakefield and colleagues published a paper in Lancet, which is a well-known British medical journal, which claimed that the MMR vaccine, which is used against measles, mumps, and rubella, caused autism in children. Although it was retracted in 2010 for being fraudulent, it had a lasting negative impact on vaccination rates. Even today, hundreds of thousands of children in the UK do not get the MMR vaccine, and many die of measles every year. Another example is in 2013, the Journal of the American Medical Association published a meta-analysis which found that slightly overweight people have lower mortality than normal weight or underweight people. That is, overweight people live longer. This was contradictory to what doctors have always believed, and it was later challenged by Harvard researchers and found to use incorrect methodology. Perhaps the most egregious example is Purdue Pharma, which used misleading charts to convince doctors that OxyContin was less addictive than it actually was. And we all know that doctors writing prescriptions for OxyContin was a major contributing factor in the opioid crisis. So not being data literate and falling prey to misinformation can have serious consequences. So how can we begin to be more data literate? This is a simple framework which I use to identify red flags, and it's mostly applicable to surveys and studies, which are among the most common data analysis formats reported in the media. So I call this 4 Ws and 1 H, and it's adapted from the 5 Ws and 1 H framework, which is used in journalism. So we start by asking what? What is the study or survey about? What is the hypothesis? Is it controversial? Does it sound too good to be true? Basically, does it pass the smell test? Next question is who funded the research? Unfortunately, a lot of the times people or organizations who fund research have ulterior motives or an agenda that they want to push, and this can taint the research. The credentials of the researchers, as well as quality of journal and publication, are also important factors to consider. Where did the data come from is another crucial question. Self-reported data, for example, is usually less trustworthy. Not having a large enough sample size or having biased samples are other common sources of error. The next question is how. So here, I don't mean for you to go deep into the methodology of a study or survey, because oftentimes that might not be accessible or easy to understand. But in most cases, the key assumptions used in the study or survey will be listed. So it's definitely worth checking to see if those seem reasonable. A study that has multiple citations and other studies which corroborate the findings are also usually more trustworthy. And finally, look at the conclusions or interpretation from the study. Usually in statistics, there's always a degree of uncertainty. So if there's a decisive call to action from a study, something like stop doing X immediately, that's usually a red flag. On the other hand, if a study is reproducible, that makes it much more robust. So let's apply this framework to the previous MMR vaccine research study example. So the first question, what is the study about? So this was a pretty controversial study because it claimed that the MMR vaccine caused autism in children, and there wasn't any prior research backing this. Who funded the research? When an investigation was conducted, it was found that there was a conflict of interest because this study was funded by an anti-vaccination group. Where did the data come from? So this study had a very small sample size. It only had 12 children. And it was also found that there was a bias in recruiting participants into the study. There were no other reputable publications with similar findings. And finally, the interpretation seemed very absolute. That is, the authors seemed very sure of their findings and didn't quantify any degree of uncertainty. So overall, applying this framework, we can see that there were quite a lot of red flags in this study. Now let's move on to misleading data visualizations, which are another popular data format used in the media. I'll start by discussing an example from my data visualization class when I was in grad school. So we were given several years of data about two futuristic political parties, Romulans and Klingons, and the government structure was similar to the current government structure in the US. So there was a House, Senate, and two main political parties. And then we were asked to create 3 simple static visualizations without changing the underlying data itself in any way. One deliberately skewed in favor of the Romulans, the second one biased towards the Klingons, and finally an unbiased fair view. So let's look at my pro-Romulan view. So here, the x-axis is time. So we're measuring over a 12-year period. And the y-axis is average unemployment. These are absolute numbers. The blue line represents Klingon presidency, and the red line is for Romulan. So if you look at this chart, it appears as if the average unemployment was much lower during the Romulan presidency compared to the Klingon presidency. However, everything is not quite as it seems, because I applied some tricks here. The first one is that I started the y-axis at about 2000 instead of 0. And this really exaggerates the difference in these numbers, making the contrast look much sharper than it actually is. So if I had started the y-axis at 0, these two lines would be much closer to one another. Second is the years of comparison are actually different. So even though I'm comparing over a 12-year period, the time periods I'm using for Klingons and Romulans are about 40 years apart. And although this is indicated under each line in the graph, it's not highlighted significantly. So the difference in unemployment here could be due to various other time-related factors, such as overall population, especially since the y-axis is absolute figures and not rates. And so it's misleading to attribute this difference to the presidency. Finally, next, let's look at the pro-Klingon view. So here, the x-axis again is time, this time in months, and the y-axis is employment, absolute numbers. So this presents a completely opposite view from the previous slide. Here it appears as if there was a significant sharp decline in employment soon after the Romulan presidency began. But once again, here the trick is the y-axis is limited to the employment range instead of starting from 0, and I'm reporting absolute employment figures instead of rates. Finally, let's look at the unbiased, balanced view. So here the y-axis is the average unemployment to employment ratio. So it's a rate, not absolute numbers. And these letters on the top represent the different Senate House combinations. And here I'm including the entire data set. So I haven't cherry-picked data as in the previous two examples. So the colors, again, blue is for Klingon presidency and red is for Romulan presidency. So the first panel here, we plot the data for this metric when the Senate and House were both Klingon. And I'm using box plots here to represent this metric presidencies. So the lines in the middle of all of these box plots represents the median of this metric, and the height of each of the box plots represents the variance. So if you look at the median across these different combinations of Senate, House, President, you can see that there's actually not a very significant difference in this metric between these different combinations, except for a few outliers. And so overall, this shows that there isn't enough data here to suggest that one particular combination of Senate, House, and President is far superior to the others when it comes to this metric. So this assignment was pretty eye-opening for me in how data visualizations can really be used to mislead people. Now I'll walk you through a few common red flags to keep in mind when looking at data visualizations in the media. The first is cherry picking. So showing only specific time periods or groups which align with your narrative. So the pro-Romulan and Klingon examples that I showed from the previous slides use cherry picking. Another common tactic is comparing different time periods. So for example, in the media, you often see charts which show year-over-year differences in some metric and then attribute a random factor and then attribute that difference to a random factor. However, this is pretty misleading because unless causality has been established, you cannot attribute differences in different time periods to any random factor. Using cumulative data instead of non-cumulative data is another tactic. So this chart on the left shows the cumulative annual revenue over a time period. And the chart on the right shows the annual revenue over the same time period. So the underlying data set is the same for both these charts. However, if you look at the left chart, it isn't as obvious that the annual revenue has actually been decreasing significantly over the years. This is much clearer on the right chart. So the left chart here is definitely misleading. Axis scale manipulation, such as truncating the y-axis or using log scale instead of linear, are other common tactics. So again, this is the same data for both these charts, but they tell pretty different stories. So if you look at the left chart, you might think that there has been a sharp increase in significant rates from 2008 to 2012. However, if you notice carefully, the y-axis here starts at 3.14% instead of starting at 0. And so if you plot the data correctly, you see that the differences are actually pretty minor and most likely not significant. Going against convention when it comes to colors is another common tactic. So usually we associate the color red with heat or warmth, whereas blue is associated with coolness or cold. So if you reverse these colors, that's likely to lead to incorrect conclusions and confusion. Finally, pie charts are notorious for being misused. Some examples include pie charts which do not add up to 100%, or including so many slices in the pie chart that it becomes difficult to compare. So these were a subset of common red flags to look out for in data visualization, but there are a whole lot more. Next, I want to do a bit of a deep dive. 3 common biases found in research studies. So if these biases exist, the findings from the study or survey are not reliable and unfortunately can lead to incorrect decisions. The first is p-hacking or inflation bias. So usually any research or experiment starts with a hypothesis. So for example, a hypothesis could be that doing X will improve metric Y by 5%. And then you compare two groups, control, which is the status quo, and treatment, which is given this y, which is given this x intervention. So the null hypothesis here is that the two groups, control and treatment, are the same when it comes to the metric y. So then you do the research, you set up the study or the experiment, and then compare the metric y between control and treatment and find that there is a difference in metric y. So p-value or probability value is a number describing how likely is it that the difference that you're seeing in metric y would have occurred by random chance, as opposed to your intervention x. That is, what is the likelihood that the null hypothesis, which was that the control and treatment are the same, is true. So obviously, the smaller the p-value, the lower the probability that the null hypothesis is true. And the standard is to use a p-value of 0.05 as the threshold. So if your p-value is less than 0.05, that means your experiment is statistically significant and you can reject the null hypothesis. So in our example, you can say that if the p-value is less than 0.05, the intervention x did indeed improve the metric y by 5%. So p-hacking occurs when you don't quite follow the scientific process. So when the objective is not to test a hypothesis, but instead to get a statistically significant result, that is called p-hacking. So usually in a well-designed experiment or study, you fix the period of time for which the experiment will run prior to starting the experiment. So if you do things like stopping the collection of data once you get a p-value less than 0.05, or conducting analysis midway through the experiments to decide whether to continue collecting data, these are examples of p-hacking. Another example is if you analyze a lot of metrics. So in our example, if instead of looking at metric y, you also look at 100 other metrics, even though you might not have had any hypothesis about those metrics, but then only report those with p-value less than 0.05, you're basically increasing the chance of false positives. And then finally, deciding whether to include or drop outliers post-analysis, or excluding, combining, or splitting treatment groups post-analysis based on whatever gives you this p-value are also examples of p-hacking, because these decisions should be made prior to doing the analysis. Selection bias is another common bias, and this results from an unrepresentative sample. So sampling bias is a type of selection bias, which has a few different flavors. Undercoverage is when some members of the population are inadequately represented in the sample. So for example, if you conduct a survey but exclude people who make below a certain income level, then your survey has sampling bias. Voluntary response bias happens because people who volunteer or self-select into a study or survey usually already have strong opinions about a specific topic, and these cannot be generalized to a larger population. Similarly, non-response bias occurs when individuals chosen for the sample are unwilling or unable to participate in the survey. Time interval bias is another example of selection bias, and this is caused by intentionally specifying a certain range of time to support the desired conclusion and ignoring the other time periods which don't support your narrative. So it's similar to cherry picking. Lastly, is the problem of confounding or lurking variables. So Simpson's paradox is a trend or result that is present when data is put into groups, but reverses or disappears when the data is combined because of hidden or lurking variables. A famous example is from UC Berkeley. So in 1973, UC Berkeley's graduate school found that they had admitted about 44% of their male applicants, but only about 35% of their female applicants. So they suspected that there was a gender bias against females in their admissions process. However, when a statistician looked at the data by department, they actually found the exact opposite. There was a statistically significant gender bias in favor of women for 4 out of the 6 departments, and no significant gender bias in the remaining 2. So the hidden variable here was department. Women tended to apply to more selective departments. Oftentimes, it's not that easy to identify these hidden or lurking variables. So one thing you can do is, instead of only looking at averages, try to look at different cuts of data. These days, there is also software available which can look through different combinations and segments of data and help identify hidden or lurking variables. With that, I want to summarize the key takeaways from my talk today. The first is to be wary of absolutes. There's almost always a degree of uncertainty in everything. And if something seems too good to be true, it often is not true. Next is to be aware of biases. We all know that humans have biases, and it is humans ultimately who are conducting research and other surveys. So we should always be cognizant of our own as well as others' biases. Don't be afraid to ask the right questions and practice asking the right questions. Applying frameworks like 5 Whys or 4 Ws and H can go a long way in this. Validate, validate, and validate. Always seek out multiple perspectives, especially those that differ from your own, because this can really help bring clarity of thought. And finally, really consciously hone your critical thinking muscle. Try to approach every question or decision in a structured manner. Mental models such as first principles thinking are particularly useful here. So with that, that's all I had for today. Thank you for listening. I hope you enjoyed the talk and found it useful. Now I'll see if there are any questions. So far we don't seem to have any questions, but I've also put together a list of references and resources if you're interested in learning more about the different biases I talked about, as well as first principles thinking and other critical thinking. Understanding more about design of experiments is also something which I would encourage learning more about. And I think another thing to mention is, so this does require quite a lot of work. So I would recommend being intentional about where you apply this framework, because if you try to apply it to literally everything you see in the media or elsewhere, it can become pretty time consuming. So if there are no more questions, feel free to add me on LinkedIn as well, and or feel free to send me a message through this platform as well.
All right, since no one seems to have any questions, thank you guys so much for coming. Have a nice day.
Yeah, thanks.